what I'd like to start out doing here is talk about some of the selenium-related research we've been doing in southern West Virginia related to a number of factors.
Do we roll it?
Okay. So we're identifying sources and effects of selenium in the Mud River as one of our first projects. Where is it coming from? How much is coming from it, from various sources and so forth. And specifically, we're trying to determine how much of the sediment-bound selenium in the upper Mud River reservoir can be attributed to discharges from Pt1. That's the big mine that stretches over the Mud River. Determine the major sources of selenium input into the water column in the Mud River watershed, and evaluate the impact of Pt1 on fish and benthic macroinvertebrates, tissue selenium concentrations, and larval developments. And this is one of several projects that I'll discuss today on selenium. And I'll roll through these pretty quickly, but would encourage this to be interactive. So in the water column sampling, we did a year's worth of sampling, 15 sites, and looked at a bunch of parameters, selenium among those, but also TDS, sulfate, pH, and so forth. Slide number 5 shows the distribution of our sampling network, not only sediments, but also the water column work. And the orange bit in the middle, that is Pt1 itself. Pt1 extends to the north and crosses the river, and the active mining is largely over on this side, although there's still some over on the north side of the river. And this is what the water column itself looks like. And this is total selenium averages. And if you walk down from site number 1, 2, and 3, those are upstream of Pt1. And then once you get to 4, 5, 6, and so forth, you're down in the, you're crossing through the Pt1 area, in the stream itself in the Mud River. And then you get out of the Hobet mining area right around sample 8. And then you're in the river downstream of Hobet. And then the blue is are some of our samples in the right fork reservoir of the mud. The mud has 2 forks on it. And then there's the left fork reservoir, the left fork river. And then for comparison purposes, we have Plum Orchard Lake, which is our reference reservoir over near Beckley, West Virginia, not mining affected. So what you see is as soon as you get into the area around Hobet, you start bouncing up well above that blue line. The blue line is about 5 micrograms per liter. I just put that in arbitrarily to give you some idea what the in-stream standard for chronic fish health ought to look like. And you start bouncing up above 10 micrograms. The scale is in milligrams, but I'll talk in micrograms. And then it gets up as high on occasion as 18 micrograms, but most of the time it's around 8 to 10 micrograms per liter. And then
I'm sorry, are all of those sites on the main stem of the Mud River?
Yes,
Okay.
all of these, until you get down to blue here. And then once you get in the reservoir itself, the concentration drops off pretty dramatically, almost always below 5 micrograms. And in the left fork, on the other hand, the site that is fed by the left fork of the Mud River, there's very little selenium, and there's very little selenium actually in the left fork of the river itself. The reservoir discharge bounces up, but it's still below 5 micrograms per liter, and it's generally around 3 to 4 micrograms per liter. And then Plum Orchard Lake has almost no selenium. So there's no question about it. The selenium here is coming from Pt1. It correlates with a number of other parameters. I'll just show total dissolved solids as an example, but sulfate, pH, all look about the same. Actually, pH does not, but TDS and sulfate look about the same. So does alkalinity. So you're starting at these 3 sites above the mining area. As you get into the mining area, TDS goes up to, the red dots are the mean values. So the averages turn out to about 1,000. Some get up 1,800 milligrams per liter or so. Then they drop off again in the lake, and then in the left fork you see very little TDS going on. This slide 8 shows the correlations. There's a high correlation between alkalinity and selenium, TDS and selenium, sulfate, even total organic carbon in the right fork. But the 3 are alkalinity, TDS, and sulfate. All are correlated with selenium. And basically that's your mountaintop mining signature. And you have negative correlations on acidity and other things like iron is very low to start with. And then you also have a negative correlation between selenium concentration, TDS, and flow. And that's what you're seeing here in slide number 9. So the more flow you get, wrote this 40 CFS here, the more your selenium comes down, even at mud sample number 6, which was right in the middle of HOBET 21. And then on the left fork, the non-selenium affected fork of the Mud River, you get almost no correlation at all. In fact, selenium's low, TDS is low, and it stays low regardless what the flow is doing. So, we wanted to see, what we're trying to ultimately do is develop at least a conceptual mass balance of where the selenium is coming from, where it's going, how much is piling up in the sediments, how much is leaving the reservoir, basically an input-output model on the reservoir itself. So we took a bunch of sediment samples. We had Stantec, a professional organization that was recommended to us by the Corps of Engineers, come in and do our sampling. They use divers, proper core equipment, and so forth. And we ran a longitudinal transect down the middle line of the thalweg, and then also took samples off to the sides near the shore, right and left sides. And we went to a maximum of 20 centimeters up into the center line, and then 5 centimeters off to the sides.
Were those composited, or were they kept separate, the side and the thalweg samples?
Oh, they were all separately analyzed, yes. So this gives you some idea at number 12 of what the Mud River looks like. This is site number 1, way up near the headwaters. Very little flow. This is moving downward. One of the things you often see in southern West Virginia, particularly late in the year, are these algal blooms in the rivers like the Mud, the Coal River, and also the reservoirs. And if you come by in October, the water's cleared up, but there's this layer of algae on the bottom. So we decided to actually sample that algae because some of the work at Kesterson and other researchers have found that algae tends to scavenge a lot of selenium in the water column and then precipitate it out ultimately on the floor. So we took some samples of algal material that we scraped off the bottom. And this is where moving down towards the lake itself. And if you see over on the right-hand side, you can actually see a lot of sunfish, bluegill beds. And then this is out in near the bottom, near the dam itself. It's a good-sized reservoir. It's about 306 acres. And it's also about 14 years old, so it's a relatively young structure. This slide shows one of the cores. Now, the total organic carbon concentration, even though this is pitch black, is only about 2 to 4, maybe 5%. So it's not what I would call peat or even histic soil, but it's enough, obviously, to turn everything black and